are ready to continue. The next presentation is going to be from Dr. Grant Hedblom from 3M, and it's going to be on environmental monitoring. So enjoy.
Yeah, thank you. I'm going to quickly share my screen and pull up the presentation for you all. Then we'll get things going. Okay, can you guys see my desktop?
We can.
And the slides? Okay,
yep, we
great.
see them.
Cool. So, hey everyone, my name is Grant Hedblom. As it was already mentioned, I'm with 3M Food Safety, and I wanted to thank you for attending this meeting on integrated environmental monitoring. So this presentation today is going to cover a number of different topics regarding environmental monitoring. This is a little bit of the introduction slide you already saw, but we'll talk about a number of different topics. But I first wanted to introduce 3M and 3M Food Safety. So our business began back in 1984 with our Petrifilm plates for quality indicator testing. And over the years, we've expanded our portfolio to include the Clean Trace system for ATP monitoring, our molecular detection system for pathogen detection, our microbial luminescence system for ultra high temperature treated beverages, and a number of different things. And all the information I'm covering today can be found in our environmental monitoring handbook, which is a great online resource you can access at 3m.com/environmental monitoring. It's a very academically focused book that kind of covers the fundamentals of an environmental monitoring program. And a lot of what I'm covering today is directly addressed in there. So highly recommend you check that out. And you can always email me. I'll put my email up at the end of the presentation. If you want a copy of this, you can shoot me an email and then I'll send you the link. So today we will cover the importance of environmental monitoring. We'll continue with sample collection, hygiene monitoring as it pertains to environmental monitoring, environmental monitoring for indicator and spoilage organisms, for pathogens, allergens, and then kind of round it out by covering the overall importance of data. So a little history lesson. So risk-based approaches to managing food safety were initially pioneered in the 60s for the space program specifically. So in the late 1960s, there was a lot of innovation and this was sort of pioneered at that point in time. And it was primarily focused on just testing the end products of the whole thing. So in the process of food production, they only focused really on the end and final products as a way to examine if food was safe or was of high quality. But over time, it became evident that end product testing necessary to provide assurance that the food was safe would be so extensive that you would actually have to discard a lot of food. So then over time, the focus had shifted from preventing hazards through product formulation and process control in a risk-based manner. So you can see here that it's shifted only, from not only focusing on the final product, but the whole spectrum of food production and understanding the risks associated with the potential hazards that are associated with the food products and the process. That is an essential part of food production. When these hazards are understood, you can then implement preventative measures to address these hazards, which will then prevent illness and injury. And this then is also a proactive and systematic approach to food safety that emphasizes preventative controls, which has now become a universally accepted part of food processing because it helps focus attention on the most important areas to prevent future food safety issues. Rather than sort of reacting to problems as they arrive, you can address them before they occur. So contamination of food products can come from a number of different sources. It can come from the people who work in the plant, the facility itself, pieces of equipment, animals, pests, and other parts of the plant environment, and even the food product itself. These can all introduce contamination into the finished product. So in order to address this, environmental monitoring is the recommended approach. You obviously take a look at the whole spectrum. And environmental monitoring involves the sampling and testing of the environment and equipment within a food manufacturing facility to prevent cross-contamination of the finished product from the environment. This should be approached holistically and encompasses a range of tests, including ATP, indicator and spoilage organisms, pathogens, and allergens, in order to ensure both food safety and quality. So you may ask, what's the goal of investing in environmental monitoring? Environmental monitoring will help you keep the food safe and wholesome and to keep your customers happy and healthy. It is important to note that advances in global surveillance methods are increasing the risk that one of these food safety events will be detected by regulators. So for example, in early 2019, 20.5% of the FDA food recalls were products that had been already distributed nationwide. This is a very, very high number. It's the highest it's ever been. And this can be attributed directly to increased surveillance methods. The other reason, you obviously want to deliver a financial return on investment to the enterprise by preventing these product recalls that can occur if they've been detected, limiting the size and scope of any recalls that may occur, and overall preventing brand damage, which in the age of social media is more important than ever, right? Because a bad image in the public eye can really, really drastically impact your brand. So environmental monitoring should be approached holistically and should not only address one of these things. You should try to consider all of them. So it should not only be ATP or only pathogen testing. It should take into account ATP testing, pathogen testing, indicator testing, and allergens in order to cover all the relevant risks to your consumers. So if we look at general guidance on how to build an environmental monitoring program, it generally looks something like this. And it applies to all those things we talked about in the last slide. It starts with identifying the correct sampling sites for the test of interest, then determining the frequency of sampling for that particular test, and then analyzing the data that you generate, following up that with root cause analyses, and then implementing corrective actions as you see necessary. So we'll now shift, and as we talked about, the first thing on the last slide is sample collection. We'll address that first. So the goal of collecting samples is to choose sites that will enable you to find the microorganisms or allergen of interest in the production environment. As you design this program, please keep in mind that the sites you choose should allow you to assess effectiveness of cleaning, sanitation, and hygiene practices. To find pathogens in the environment before they can contaminate the product, and to also find spoilage microorganisms in the environment before they affect the end product. So there are a few things I'll be covering with regard to sample collection. Number one, sampling possible harborage sites or growth niches in your equipment or the production environment. Number two would be determining the frequency of sampling. And then number three would be ensuring that you are using the correct collection device to actually get that sample, and that your collectors are properly trained in how to use that device. A really essential thing to consider when we're discussing how to collect a sample, where to sample, and how frequently to sample is zoning, or the concept of hygienic zones. Not hygienic zoning, this is a little different. So as you begin the planning process, we need to figure out what you would consider to be zones 1, 2, 3, and 4. And I'll detail each of the zones one by one. So zone 1, these are the surfaces directly in contact with the food that is being produced or in which the food is being exposed. So this is stuff that's coming directly in contact with food. Zone 2 are non-food contact surfaces that are adjacent to zone 1. So these can be control panels on pieces of machinery or equipment frames. You know, they're not directly touching the food, but they're in close proximity and they should be tested. Zone 3 are non-food contact surfaces that are located in or nearby processing areas, such as the floors, the walls, drains, ceilings, etc. And then zone 4 are areas that are completely outside the production area. These can be break rooms, parts of the building that are completely separated from the production floor. And multiple sampling sites from each zone should be selected before you begin taking samples as a part of your program. An environmental monitoring program can also play a key role in not only improving the safety of the food products, but also can help you to identify, manage, and eliminate growth niches. And just to clarify and give a definition, growth niches are areas that can support overall bacterial growth. These could be cracks, crevices, hard to reach areas, nooks and crannies in the production area. And these areas are often protected from the sanitation and cleaning process. And if you see high microbial counts, even after cleaning and sanitation, this may be an indication that this area is a harborage site. And nutrients from the food and water can actually be trapped in these growth niches and sort of serve as a really, really optimal place for bacteria to grow and for biofilm formation to occur. So these can be once they develop, they can be very, very hard to get rid of. So an environmental monitoring program can help to identify those growth niches and help you address them and get rid of them to overall improve the safety of your product. So we'll then now kind of shift gears and talk about how you will select what device to use and how to then collect your sample. So collecting environmental samples in a sterile and aseptic manner is super critical to ensuring the quality of the testing results and is essential for you to do. And you must train your technicians and help them be mindful of using sterile technique because you want an accurate result. Equally important is choosing the right tool for the job or the correct sample collection device for the sampling site. So the devices that you choose should effectively, as you can see on this sort of table here, reach the sample target area. They should be able to aseptically collect the sample, dislodge any microbes on the surface, and effectively neutralize any residual sanitizers that may be remaining on that surface. So when it comes to sample collection, there are two major types of sample collection devices you can choose from, sponges or swabs. Sponges are larger sampling devices that come in a variety of different neutralizing buffers and formats, and they are the preferred choice for when the area that you're sampling is relatively large and readily accessible, and for when qualitative pathogen testing is to be conducted, sorry. Swabs are obviously smaller in size that, due to their smaller size and ease of use, are preferred for reaching those crevices, nooks and crannies, et cetera, and are particularly useful for quantitative environmental testing, such as indicator testing and something that will provide you a CFU reading. But you don't have to limit yourself specifically to these just general cases. You may need to use a swab to find a pathogen, given the sort of the make or the nooks and crannies of where you're trying to sample. But you also may need a sponge to get a better representation for indicator testing. They're not hard and fast, but these are just sort of the general rules we advise for choosing between the two devices. So guidance for sampling frequency and the number of samples suggests that you need to be determining your sampling based on risk. So as you can see in this table, areas that are hard to clean and also pose a large hazard to the overall quality and safety of the foods you're producing should be sampled frequently. Whereas areas that are easy to clean and are not very hazardous to the overall production and quality of food only require a relatively low frequency of testing. So generally, sites where the food is exposed to the environment are considered high risk and would require you to do more frequent sampling. But it's also important to keep in mind which part of the process the sampling site is located. The risk and the frequency of testing may be lower for equipment in a raw production area and more stringent and rigorous in a finished product or a ready to eat area. Obviously, you want to make sure that that food is not getting contaminated because you're shipping it and assuming that the customer can eat it right away. Areas or sites in which environmental monitoring results frequently reveal poor sanitation or emerging microbial harborage sites may bring about an increase in frequency of sampling until the environment has been stabilized. And another couple things to consider and that might increase the rate at which you sample, is obviously the size of the facility, the pace of your production, and then the overall age of the facility and the equipment. As these factors increase, like if your facility is bigger, your production rate increases, you may want to increase your sampling to reflect that. So we'll next shift gears and talk specifically about hygiene monitoring. So a lot of people mix up exactly what cleaning and sanitation are, or assume that they're sort of a one and the same process, but there are distinct differences in functions between the two operations. Cleaning involves the removal of soil and debris from surfaces, whereas sanitation involves the reduction of microorganisms that may be contaminating that surface. Cleaning and sanitation are part of the manufacturing process, and just like other processes, such as mixing, baking, packaging, you'll want to monitor and manage them for quality and optimization. So cleaning and sanitation are interconnected and interwoven, and effective cleaning then sort of paves the way for effective sanitation. If you have to clean the surface, obviously with cleaning, you'll have to clean the surface first. And the majority of this regime should focus on your cleaning. So cleaning involves the physical removal of that debris and will improve the efficacy of your sanitizers to actually get to the bacteria or organisms of interest and inactivate those contaminants. Think of sanitation as sort of the finishing step of actually killing the bacteria, whereas the cleaning is doing most of the work otherwise. And without cleaning, the efficacy of your sanitizers goes drastically down. You'll have to apply more, you'll have to pay more, you'll have to use more to get that same effect as you would if you had a better cleaning protocol. And when you don't do a good job of cleaning and sanitation, you can have lower microbial quality and higher risk pathogens entering your finished product. And this can ultimately reach a point where your product is no longer sellable because it is spoiling too quickly or your shelf life has been drastically reduced. So a thorough hygiene monitoring program is multifaceted and should include multiple methods for collecting data. So microtesting, visual inspection, and ATP testing are not comprehensive individually, but when used together, they can give you valuable insights into the effectiveness of your cleaning and sanitation programs and can be tools for cleaning verification. It is also important to note that microbial testing or microbiological testing is a verification of the sanitation process and not the cleaning process. So doing total plate count and everything, that tests your sanitizer, whereas visual inspection and ATP test your cleaning. When a monitoring procedure does not involve a quantitative measurement, such as like what you would get with an ATP measurement, it should be typically coupled with a strong verification strategy. So for example, if you are doing visual inspection or visual observation of equipment for cleanliness, you should verify that process through periodic testing using an ATP monitoring system, because just because something looks clean doesn't always mean that it actually is. And so, as we talked about in the last slide, ATP is commonly used for this purpose. So ATP, or adenosine triphosphate, is an energy carrier molecule that is present in every single cell. And as well as being present in these living cells, it is present in residues from organic sources, such as your foods, from bacterial biofilms or surfaces that are contaminated by technicians by putting their hands on them. There are all situations, these are all different situations where you will overall promote microbial growth, which can thereby increase the risk to safety and quality of your foods. So ATP is a really good way to examine the overall numerical or assign a quantitative value to the effectiveness of your cleaning of surfaces. So we're going to quickly outline a couple steps in how you create an ATP monitoring program. So the first step is going to be involving you getting your team together using QA and sanitation. And you should primarily focus on zones 1 and 2 that I talked about before. From there, when you've sort of identified those zones 1 and 2, you want to create a master list of test points, which can vary between 100 to 500 different test points, depending on your facility and the equipment you use. And you should also try to compile as much relevant information on those test sites as possible. So you can see, building, line, a number of different pieces of data that you can track and trend. So when it comes to the test selection process, a couple slides ago, we reviewed the risk-based approach using this table of probability and hazard, keeping in mind that the aim is to assess cleanliness and control the overall risks that are posed by having an unclean surface. So that table is nice, but I think it's more helpful to look at it specifically with a piece of equipment like this meat slicer. So to better understand the concept, let's take a look at some of these possible sampling sites. So within a single piece of equipment, you can have obviously a number of different sampling sites. But if we only focus on like the collection pan and the collection side, the components of this meat slicer, because they are easy to clean, you would thereby be missing some of the more important sampling sites, such as the blades that comes into direct contact with the food you're processing, or the tray that collects the sliced meat. These may pose, or these will possess a higher risk to your overall food quality if they are not cleaned properly, because obviously they're a little bit more difficult to clean, but they are coming into a high frequency of contact with your food. So you want to make sure you're addressing those often. And so after verifying the effectiveness of cleaning by doing daily ATP testing for all those sites, then the sites can be rotated then for daily sampling. So once an acceptable data set or your test sites have been obtained, and this can take a little while to collect the sufficient data. This can take up to like 30 cleaning cycles. The pass-fail levels for these different sites can be determined. And so once you sort of determine the pass-fail limits for these sites, you can then go on to determine and sort of develop your baselines. The next step is then regular verification of cleaning. So after the validation for pass-fail levels for those different sites, it is common then for you to take a randomized approach to this testing. So instead of testing all of them, you'll kind of pick some or randomize your testing to swab a smaller portion of all those possible test sites. And you can randomize them by risk. So obviously some of those higher risk ones you'll want to test more frequently. But yeah, you'll want to basically decide how you want to then follow up and examine them. You obviously don't need to test all 100 to 500 test sites every single time. You can take a risk-based approach to examining them. And then in the event that you get a failing result, you can implement corrections and document it as a part of your system. So this is a way that you can develop your baseline, understand what might be above normal for one of these readings, and then you can follow that up with corrective actions or changes to your process. In the case of hygiene monitoring, a failed test outcome will typically result in re-cleaning and retesting that surface until you achieve a pass. And then the fourth and final step is to track and trend that data. So a lot of ATP system manufacturers, such as ourselves at 3M, will provide a software for managing that data. So you'll take all these readings, you can manage the data, and you can then examine this and essentially analyze this data with a task force and conduct root cause analyses to identify possible ways you can improve your process and improve the control of the environment. So when you're trending and analyzing this data, aspects that should be routinely monitored should be like your cleaning consistency, suitability of those pass-fail limits, seeing if they may need to be modified over time, looking for trends or patterns of different areas of concern. So once you've kind of gone through this whole process of selecting your test points, getting a lot of data, determining your baselines, and then testing it randomized, you can then begin to see very effective trends and then impact or then change or modify your procedures. So that's sort of what this slide is highlighting here. You can see on the graph on the left, this is a situation that's sort of out of control. You have a kind of jittery baseline. It jumps up to failing results every once in a while. And this is something that would be a failure, but you could obviously course correct and change it. But the more you kind of trend and examine this data over time, you can see, like on the graph on the right, it's a very, very stable baseline. This is a situation where the cleaning efforts are very under control. And then the occasional high peak or something is an exception rather than the norm. So once you've trended this data and you are actively monitoring it and making modifications to your cleaning procedures, then you can then have a stable baseline for your ATP system. So now that we've kind of covered hygiene monitoring and sample collection, we'll talk about environmental monitoring for indicator and spoilage organisms. So some of you may be thinking, if I use ATP, why would I then need to perform testing for indicator organisms? These types of testing address two separate things. ATP verifies cleaning, and indicators verify the effectiveness of sanitation protocols. So, sanitizers are obviously used with the goal of killing off organisms. Using an indicator test will help you understand if those organisms have survived the sanitizers. Additionally, organisms can exist in sites where sanitizer can't reach. And if the processing environment is under control, the indicators will also be under control. So in addition to being a critical part of sanitation verification, indicator organisms provide information on the hygienic status of the processing equipment. So the most common groups of organisms that are tested are the total plate count or the total aerobic count, and coliforms and or Enterobacteriaceae. Total plate count is used as an indicator of overall sanitation, while coliforms and Enterobacteriaceae are used to identify hygienic conditions and sanitation effectiveness. So including spoilage organisms, not only just indicators, but spoilage organisms in your environmental monitoring program can also allow you to be proactive and address potential spoilage problems, which can lead to decreased shelf life and off flavors. So these include lactic acid bacteria, which can lead to off flavors, slime, off odors, or gas production, or you can include yeast and molds. Yeast and molds are often very difficult to eradicate, as the source of yeast and mold contamination is more often than not the air in the facility. So in general, your process, food product, and other factors such as your plant will often dictate which groups of organisms are most relevant for your production environment and your facility, and which ones should be included in your program. So similarly to how we did with the ATP monitoring, you'll want to first identify different sites that you want to check for these indicator organisms. So when you're checking for indicators, the most common zones, just like with your ATP, are zones 1 and 2. So depending on your facility, testing in zone 3 can more often than not cause sporadic results that have no obvious trending. And testing in zone 3 for indicator organisms can more often be used for like a root cause analysis or trying to identify some of those growth niches. And spoilage organism testing overall is more so done in zones 1 and 2. And then you would perform something more like an air sampling for yeast and mold in zone 3. So when choosing sampling sites for this indicator testing and spoilage organism testing, it's important to consider the potential sources of contamination, such as cross-contamination of sources outside of the production area, ingredients and raw materials, atypical activities, such as changes in the cleaning chemicals, and several other different sources. Sampling sites for indicators and spoilage organisms should be representative of the overall process step. So different materials will need to be taken into consideration. So a large, flat stainless steel surface is going to be obviously easier to clean than something like a fabric-lined belt. So on the left, there's this diagram of an example processing area. And in this example, you can begin to think about possible sources of contamination and the best sampling sites. So because this line is exposed to the air, I want to do some air sampling for yeast and mold near the line to make sure that the sample quality is good. And then you can see that this dead leg can be very difficult to clean and can harbor bacteria. So that would be something to test with some frequency. But let's take a little bit and kind of zoom in specifically on that conveyor belt. So the conveyor belt obviously has different components. So the slats that you see running across the conveyor belt are a larger surface that are, I would say easier to clean than some of the other components. So for those larger surfaces, we would recommend using a sponge or even some direct contact testing to get your indicator samples. However, sampling in between those slats, like you can see sort of in this joint here, is more difficult to reach. And in that circumstance, it may be better off to use a swab to get in there and get into that nook and cranny. So in your environmental monitoring sampling plan, you want to be sure to note in which part of your operation to collect samples, along with sampling sites and overall frequency. So for example, after each sanitation cycle and before starting production, it could be pre-production, such as running the equipment before sampling to have a better chance of collecting those residual microorganisms that may have remained after you've applied your sanitizers. You could do it during production, ideally, like 3 to 4 hours into a run, so well into a production run, or at multiple time points. Or you can perform this indicator testing and after non-routine activities. So if there's been any changes, or if you're adding machinery, moving things around, performing maintenance, or have construction projects, you'll want to do more indicator testing at that point to kind of understand how those changes have affected the microbial balance of your facility. So one of the key benefits to performing indicator testing is that they will provide you with quantitative results. And you can use that quantitative data to monitor for trends over time. So you can examine if something is trending upwards or downwards based off these quantitative results. And these can benefit your facility by helping you identify failure points that can trigger future investigations. They can allow you to act before a failure is reached. You can gain a greater understanding of different seasonal effects and can help you identify opportunities to improve your process. So we're going to now shift gears and briefly talk about environmental monitoring for pathogens. So a pathogen environmental monitoring program is not a pathogen control program. They're two separate sort of things. A pathogen environmental monitoring program is an ongoing measure of the effectiveness of the overall pathogen control program, and ultimately serves as a verification program of your pathogen control program. And it serves to give you feedback on where and when efforts need to be directed for the overall pathogen control program. This verification program will be plant dependent, and there's not sort of a one size fits all solution that works for every single producer when it comes to performing this pathogen testing. So that's important to consider, is that just because one facility does it this way doesn't necessarily mean that that's the best fit for your facility or your production environment. So there are a considerable number of pathogenic microorganisms that can cause foodborne illness. However, just a few have actually been associated with environmental sources linked to foodborne illness. So some of these include Listeria monocytogenes. Although most pathogen testing is just done for all Listeria species, Salmonella, and Chronobacter. So Chronobacter is an organism of particular interest in the powdered infant formula or powdered foods markets. So as you develop your pathogen environmental monitoring program, you need to assemble a team that brings together different perspectives and expertises. A strong pathogen environmental monitoring program should be constructed following a risk-based approach. And just like any of the other plans we talked about, it needs to be well documented, reviewed, and fine-tuned from time to time. So let's take a look at some of the key parameters of a pathogen environmental monitoring program. Start with determining the risk as we did for the ATP or the indicators. What organisms will you be testing for? That's an essential question to address when it comes to pathogens, because pathogen methods are organism specific. So you need to determine what organisms you'll be testing for. And this can depend on the product that you're making and the associated processing steps. Within this plan, it is also important that you identify regulatory and potential customer requirements that you'll have to meet when it comes to this pathogen testing. The next step is to determine what you are testing. So are you using sponge or swab samples? Are you using a scraping material? Are you doing product residue? It is important to maintain your sample after you've collected it until you've tested it. And it is also very necessary to establish a robust training program for your sample collectors, just as we mentioned before. Aseptic technique, making sure they know what they're doing and storing the swabs and environmental samples correctly until they can be processed. Site selection should also be risk-based, as we have reviewed, for the other types of testing. The entire plant should be explored and mapped out, looking at different areas, and all potential sampling sites should be determined, considering what may be a potential growth niche and what are potential sites of accumulation. And as I mentioned for these in the past, all sites should be covered under a master list. And making this list does not mean that all sites have to be sampled all the time, and you can randomize it just like we did with our ATP testing. So once your team has mapped out the hygienic zones in this manufacturing facility, you then want to select the specific sites. So environmental sampling for pathogens is routinely conducted in zones 2 and 3, and sometimes even 4. Zone 1 surfaces are obviously, as we talked about before, reserved for sort of ATP and indicator testing, and only under special situations are zone 1s or the zone 1 surfaces, those direct food contact surfaces, tested for pathogens. They could be tested for pathogens. However, anytime you test these zone 1s for pathogens, you would need to then implement a stringent product hold until your results are received, because if you got a positive for salmonella on a zone 1 sample, that means more than likely all of the product that you processed between testing may have been contaminated. So you'll need to hold product. And that's why oftentimes pathogen testing isn't done in zones, in zone 1. And the number and location of environmental samples is taken, or the number and location of environmental samples is determined by the risk levels inherent to the production of the process. So areas with water use or high traffic, history, if it has a history of a pathogen positive result, those are areas that you'll want to sample more frequently. And when it comes to sampling, this is sort of going back to what we talked about before with sponges and swabs. A lot of people abide by sort of this square inch or centimeter mentality and think that all samples have to be taken in sort of that 12-inch by 12-inch square. But it's important that you consider that these are just sort of these guidelines for sample collection, and not all of these potential hazardous areas in your facility will fit this mold. It is important to provide training on sampling that emphasizes the need to sample potential niches and not only just those flat areas. So really drilling down, finding what are the actual areas of risk. And as we talked about before, sometimes you may want to use a swab, sometimes you may want to use a sponge. Be flexible to address whatever you think are those high-risk areas. So you've sampled, you've tested, and now you've gotten a positive pathogen result. Your first reaction to this should never be, oh no, what do we do now? When you create your pathogen environmental monitoring program, you should always consider this as a possibility for this testing and have an action plan ready to go in place it does occur. In case it does occur, sorry. Do not even start testing for pathogens in your environment if you don't have a plan. And your plan should have, you should basically have a pathogen plan ready that states your action plan for immediate corrective actions by zones, an action plan to verify the absence of the pathogen from that area, and an action plan to execute a root cause analysis, and then to establish preventative actions moving forward. So if you find a positive result in any sampling zone, that area needs to be thoroughly examined, both through visual inspection and through vector swabbing to determine the extent of contamination. So vector swabbing, as you can sort of see in this diagram here, entails taking additional multiple environmental samples around that initial positive site in what we call sort of a starburst pattern. So sort of irradiating out from that central point. You want to take a bunch of different swabs, 10 to 15 around that area, to determine, sort of where these harborage sites are. You never want to pool these samples into one, because then you don't know where specifically it is. So you're trying to map out on this specifically where those pathogens are collected or where they're living, so you can eradicate them and address that moving forward. Sort of wrapping it out, we'll quickly cover allergens. I know I'm running up against the sort of the 1:15 mark here, so we'll cover allergens pretty quickly. Food recalls due to allergens obviously have a very drastic financial and public health impact due to, as we talked about earlier on, the direct cost of recalling products, but it also can lead to that brand damage. And to date, based on some data generated by the governmental agencies like the FDA and USDA, undeclared allergens are the most common cause of food recalls, with about 47% of total recalls. So this is outweighing salmonella, listeria, other pathogens, or even foreign material. This is by far what causes the most recalls of food products. And if we look at the cause of the recalls, it is often found that these events are related to changes in formulations that were not adequately communicated within the company. They can also be labeling errors, such as using the wrong packaging or the wrong terminology, and then from cross-contamination. Preventing cross-contamination with food allergens should be contemplated within your environmental monitoring program. So considering that in your program along with pathogens, ATP, the stuff we talked about before. For this allergen testing, we recommend that you can use it to verify that your cleaning protocols are actually removing protein residues and not just biological residues, and that these residues are being removed so they cannot and will not contaminate an allergen-free product. When you lay out your allergen controls within your food safety plan, you will likely start by conducting a risk assessment, as we do with all these other ones, finding your sampling sites. Once those risks are identified, you can then determine what controls can be implemented to prevent cross-contamination with allergens. So what can you do in your process? And finally, you must work on risk communication. So how do you train and educate your personnel in the plant to make sure that they follow those implemented procedures and how to declare allergens on a label if they are present? So allergen testing as a part of your environmental monitoring program is a tool that can be utilized and as an important allergen management verification strategy. I'm going to skip through that super quick, just for the sake of time. So if you do find an allergen protein in a site, you will need to conduct a root cause analysis and implement corrective actions. So if the site was zone 1 or 2, one question you may ask during the investigation was, how did the cleaning fail? If you are uncertain how this cleaning process failed, it's helpful to refer to one of the components here. We call it TACT, which stands for time, action, chemical, and temperature. So if this, determining was there enough time to allow for effective cleaning? Was there enough mechanical action to remove the allergen from the surface? Were you using the right chemicals? Was the temperature too hot, too cold? Answering these questions can oftentimes help you address how these allergens were introduced into your environment. And then I want to finally kind of cover the importance of trending data. And this is sort of where the rubber hits the road. So during an integrated environmental monitoring program, you're going to get a ton of information. So you can look at this example here with this ATP data. At first, it's just a bunch of numbers. But when you put the data into context, or put it into context by analyzing its performance over time, the data then can become valuable information that will talk to you visually. So you can identify patterns, frequency. You could see in this circumstance, something's happening on a weekly basis on this graph. You can see that there are spikes roughly every week. And then by applying your experience, expertise, and knowledge to that information you develop, you can then figure out a sequence of specific actions and corrective actions to mitigate those risks moving forward. So this applies to all of it: pathogens, indicators, allergens. When you track it over time, you develop an opportunity to gain actionable information, which will improve your environmental monitoring program's health and the health of your consumers. So one final thing, it's not just one of them. Environmental monitoring is ATP, pathogens, allergens, indicators. Addressing all of them will ensure the safety and quality of your products, and examining them and trending them over time allows you to drive continuous improvement and impact and ultimately benefit your customers. So yeah, I got in there at 12:15 or 1:15 exactly. I don't know if we have time for questions. If you want to email me any questions and you don't want to just ask them here, you can feel free to email me right here, but I will stop presenting and turn the reins over back to the group here. Does Toria or Christina, do we have time for questions, or do we want to keep going on to the next presentation?
No, if there's anybody that has questions, feel free to ask, or you can email Dr. Hedblom, either one. So if you have any questions. If there are none, here's the QR code, so you can do your survey. If not, email, I'm sure he can answer anything. It's obviously a topic that we are all going to see part of at some point, with FSMA and everything that's going on. So if not, I would like to thank you for joining us today.
Thank you.
Lots of good information. Thank you.